All right, buckle up, everybody, because today we are taking a deep dive into black holes. And I've got to say, the research you sent over is, well, it's pretty mind-blowing.
Well, black holes, they really are the ultimate enigma, aren't they? Pushing the limits of physics as we know it.
Yeah, no kidding. I'm already feeling a little bit of that existential dread just thinking about them.
Hmm.
So let's start with the basics, I guess. I mean, we've all seen the sci-fi movies, right? Black holes as these giant cosmic vacuum cleaners just sucking up everything in sight. But what actually is it that makes a black hole different? Like, how is it different from just a really, really massive star?
It's all about density. Like, imagine taking our sun, right, which is already huge, obviously. Now try to squeeze it all down, compress it into, like, the size of a small town.
Whoa.
That's the kind of insane density we're talking about. And that creates a gravitational pull so strong that it warps the very fabric of space and time. Literally nothing, not even light, can escape it.
So it's not really about sucking things in like a vacuum cleaner then. It's more about this warping of space-time.
Exactly. And the point of no return, that boundary, that's what we call the event horizon, anything crosses that line, it's gone. No coming back.
Like a one-way door to, well, who knows where. Okay, so I'm trying to picture this. If I was, I don't know, watching a spaceship fall into a black hole, what would it look like?
Well, it would be a wild ride for sure. As the ship gets closer and closer to the event horizon, it would start to look like it's slowing down, and the color would shift too, towards the red end of the spectrum.
Hmm.
And then as it hits that event horizon, it's like it just freezes in time, stuck forever.
Forever. But what about the people on the ship? Are they just frozen there too? Like forever?
Well, for them, inside the ship, time would keep ticking along like normal. They wouldn't notice anything different, at least not at first.
Wow. So it's like two different realities depending on where you are.
Mm.
But we can't talk about black holes without talking about the singularity, can we? That point at the center where everything gets crushed.
Ah, yes, the singularity, where all our current physics just goes out the window. We're talking infinite density. It's a point where all the matter, everything that falls into the black hole, gets squeezed into, well, a region of space-time that we can't even describe with our current understanding.
Okay, I'm definitely getting lost in the weeds here, but, how do these things even form in the first place? Where do black holes come from?
Well, the most common way, we think, is from the death of really, really massive stars. You see, stars, they're in this constant battle, right? Between their own gravity trying to crush them inwards and the energy from nuclear fusion pushing outwards. It's like a cosmic tug of war.
Okay, I can picture that. So what happens?
Well, eventually the star runs out of fuel. That outward pressure stops, and gravity wins. The core of the star collapses. Now, sometimes this leads to a supernova, this massive explosion that's brighter than entire galaxies.
Oh, right, supernovas. Those are incredible. So that's what happens when a star dies.
Sometimes, yeah. But for those really, really massive stars, the core, it just keeps collapsing, keeps getting denser and denser, and that's how a black hole is born, from the ashes of a dying star.
So from a giant star to this incredibly tiny, dense point in space, it's hard to wrap my head around it. But, you mentioned earlier that there are different types of black holes. What are we talking about here? Like, what's the black hole variety show look like?
Well, you've got your stellar mass black holes, those are the ones we've been talking about, born from a single star collapsing. But then you've got the real heavyweights, the supermassive black holes.
Supermassive. How big are we talking here?
Millions, billions even, times the mass of our sun. And these monsters, they're at the center of most galaxies, including our own Milky Way.
Wait, there's a supermassive black hole at the center of our galaxy.
Right in the middle, yeah. It's called Sagittarius A. Millions of times the mass of our sun. We can't see it directly, of course, but we know it's there.
That's a little unsettling, but also kind of awesome. But, okay, so we've got the smaller ones, the supermassive ones. Are there any in-betweens?
There are, yeah. We call them intermediate mass black holes. They're somewhere in between. Not quite as massive as the supermassive ones, but definitely bigger than those stellar mass black holes.
So it's like a whole black hole family then,
Yeah.
from tiny to, well, unimaginably huge.
Exactly. And it's this diversity, this whole range of sizes and types that makes studying them so fascinating. They really give us a glimpse into the most extreme environments in the universe.
All right, so we've covered the basics, right? What black holes are, how they form, the different types out there. But I'm really curious about what happens around a black hole. Is it just a big empty void? Or is there something else going on?
Oh, it's definitely not empty. The region around a black hole is actually incredibly dynamic, incredibly energetic. One of the coolest things is what we call an accretion disk.
Accretion disk. That sounds like something out of Star Trek.
Well, it kind of is. It's this swirling disk of gas and dust spiraling in towards the event horizon of the black hole. Like, imagine a giant cosmic whirlpool.
Okay, I can picture that. But why is it glowing? What makes it light up?
Well, as all that material spirals in, it gets squeezed and heated to, like, millions of degrees. Friction, basically. And that superheated material, it blasts out all sorts of radiation, including X-rays, which we can detect.
So even though we can't see the black hole itself, we can see the light show happening around it.
Precisely. It's like seeing the shadow of the black hole outlined by this incredible, intense radiation. And it's not just a show, either. This accretion disk, it plays a huge role in how black holes grow, how they interact with the stuff around them.
All right, so we've got this incredible light show, a cosmic whirlpool happening around the black hole. But I have a feeling that things get even weirder when we start talking about Einstein's theory of relativity, right?
Oh, you have no idea. Einstein's theory predicts some truly mind-bending stuff near a black hole, especially when it comes to time. You ready for this?
Hit me with it. I think my brain is warmed up enough by now.
All right, so time dilation. Basically, the closer you are to a black hole, the slower time moves for you compared to someone further away. It's like being in a different time zone, but on a cosmic scale.
Okay, so let's go back to that spaceship falling into the black hole. We talked about it looking like it freezes from our perspective. But for the people on the ship, what's happening to their experience of time?
For them, time would keep flowing normally. They wouldn't feel any different. But for us, watching from a distance, it would look like they're moving slower and slower as they approach the event horizon.
So two different timelines
Yeah.
running at different speeds. I'm trying to wrap my head around that, and my brain is starting to hurt a little.
It's definitely one of those concepts that takes a while to sink in, but it's all a consequence of how gravity warps space-time near a black hole. It's like a cosmic funhouse mirror.
Okay, I think my brain needs a little break before we venture into the funhouse. But before we move on, I have to ask about that incredible image. You know, the first ever image of a black hole. How did they even do that?
Ah, yes. That was a huge accomplishment. Remember, black holes themselves, they don't emit light. So for the longest time, taking a picture seemed impossible.
So what did they do? Was it just one super powerful telescope?
It actually took a network of telescopes all around the world working together. They combined their data to create what's essentially a virtual telescope the size of the entire Earth.
Wow, a telescope the size of Earth. That's insane.
Yeah.
And what did they see? I remember the image being kind of blurry.
Yeah, it wasn't the sharpest picture, but it was still incredible. It showed this bright ring of light surrounding a dark center. That ring, that was the superheated gas in the accretion disk, glowing as it spirals inward. And that dark center, that was the shadow of the black hole itself, the event horizon.
So we were basically seeing the silhouette of the point of no return. That must have been an amazing moment for the scientists involved.
Absolutely. It was the first direct visual confirmation of black holes. Like, Einstein predicted them 100 years ago, but actually seeing one, that was something else.
Okay, so we've covered a lot of ground here. We talked about what black holes are, how they form, all the wild stuff happening around them, and even that incredible image of the event horizon. But honestly, I feel like we've only scratched the surface.
You're right. We've just begun to explore these amazing objects. So where do you want to dive in next?
I think I'm ready to tackle what happens inside a black hole. You mentioned the singularity, where physics breaks down. I mean, what does that even mean?
That's a great question, and one that leads us into some seriously mind-bending territory. The singularity, huh? It really is one of the biggest mysteries in physics. I mean, try to imagine all the matter in a black hole crushed down to a single point. Our current theories, they just can't handle that kind of extreme density, that kind of gravity.
So at the center of a black hole, everything we know about physics, it just stops working.
Pretty much, yeah. It's like the ultimate limit, where our understanding of space, time, even cause and effect, it all breaks down.
Okay, but if we can't even describe what's happening there, how can scientists even begin to study it?
Hmm.
Is it all just like wild guesses at this point?
It's definitely a challenge, no doubt. But physicists, they love a good challenge. One of the most promising approaches is to try and combine Einstein's theory of general relativity, that's the one about gravity, with quantum mechanics, which describes the really, really tiny stuff.
Right, quantum mechanics. That's the one with all the weird counterintuitive stuff, right? Like particles being in two places at once.
Exactly. And bringing those two theories together, that's the holy grail of physics. It's what we call a theory of quantum gravity.
If we could crack that, what then?
Well, a theory of quantum gravity, it could potentially unlock the secrets of the singularity. maybe even help us understand the Big Bang itself. It could change everything.
Wow, that's huge. But, before we go and solve all the mysteries of the universe, I have to ask, what happens to all the stuff that falls into a black hole? I mean, does it just get crushed at the singularity, disappear forever?
That's a question that's been bugging physicists for a long time.
Hmm.
And it leads to this idea called the information paradox.
Information paradox. Okay, I'm intrigued. Tell me more.
So, quantum mechanics, it says that information can never be truly lost, like ever. But then we have black holes, right? Swallowing up everything that crosses the event horizon. It's like they're erasing information from the
So
universe.
it's like a cosmic shredder destroying everything it eats.
Yeah.
But wouldn't that contradict what we know about quantum mechanics?
Exactly. That's the paradox. And it's led to some pretty wild theories trying to explain it.
Like what?
Well, some physicists think that the information isn't actually destroyed. They think it might be encoded on the surface of the event horizon like a giant cosmic hologram.
Hold on, a hologram of everything that ever fell into the black hole.
It's a pretty mind-blowing idea, right? And it's not the only one out there. Some think the information is preserved inside the singularity itself, but in a way we can't even comprehend.
So, like, it's still there, but locked away, where our current understanding of physics just can't reach.
That's one way to think about it, yeah. It's a puzzle that's still very much unsolved. And it really shows us just how much we still don't know about black holes.
Well, I'm definitely feeling the limits of my own brain power here. But before we wrap up this whole singularity discussion, I have to ask, what about all those ideas about wormholes and other dimensions? Is there any chance those could be real?
Ah, yes. The idea of black holes as gateways to other parts of the universe or even other universes entirely, it's a really cool concept, right? And it's not completely out there.
So there's some science behind it then.
Well, wormholes, they are theoretically possible based on Einstein's equations. They're like tunnels through space-time, shortcuts between distant parts of the universe. But so far, they're still just theoretical. We haven't actually observed any.
So the math says they could exist, but we don't know for sure.
Right. And even if they do exist, using a black hole as a portal might not be the best idea. I mean, the gravity is so strong, the singularity, I don't think you'd survive the trip.
Yeah, that's probably not something I'm going to put on my bucket list anytime soon.
Yeah.
But it's still fun to think about the possibilities.
Yeah.
But okay, let's shift gears a bit here. We've been talking a lot about what's happening inside black holes, but what about their role in, like, the bigger picture, the evolution of galaxies and stuff?
Oh, black holes are definitely not just these isolated things, just sitting there doing their own thing. They actually play a huge role in shaping galaxies, influencing how they change over billions of years.
So they're not just these cosmic vacuum cleaners sucking up everything in sight.
Not at all. One of the main ways they influence galaxies is through their gravity. They act like a giant anchor holding everything together, influencing how stars and gas clouds move around.
So like a cosmic traffic cop directing the flow of stuff in the galaxy.
Yeah, kind of like that. And they also release a ton of energy in these powerful jets.
Oh, right, jets. Those are like beams of particles, right, shooting out from the black hole.
That's it. Streams of superheated, super fast particles blasted out by the black hole's magnetic fields. It's like a cosmic fire hose shooting energy across vast distances.
Wow, okay, so black holes, they're not just sucking things in, they're blasting things out too.
Exactly. And those jets, they can have a big impact on the galaxy around them. They can heat up gas clouds, preventing them from forming new stars, or they can even trigger star formation in other areas by compressing the gas and dust.
So they can create and destroy. It's like they have a dual personality or something.
It's all about balance, right? They play this complex, multifaceted role in how galaxies evolve. They can stimulate growth, but also suppress it, depending on the circumstances.
Man, it's incredible to think that these things, these black holes, which we used to think of as just these weird, destructive objects, they're actually essential to how galaxies form and change over time.
It really shows you just how interconnected everything is in the universe, right? Black holes, they're woven into the very fabric of the cosmos, influencing the life and death of stars and galaxies over billions of years.
It makes you think about our own galaxy, the Milky Way. We know it has a supermassive black hole at its center. What's its role been in shaping the galaxy we see today?
Well, astronomers think that Sagittarius A, the supermassive black hole at the center of the Milky Way, has been crucial in shaping the galaxy's structure over billions of years. Its gravity, for instance, has probably helped to create the spiral arms we see, and it influences the rate at which new stars are born.
So the Milky Way, with all its stars, its beauty, it's all thanks in part to this giant black hole at its heart.
Exactly. And while black holes can be destructive, they're also architects of the universe, shaping the galaxies we see and influencing the very fabric of space-time.
It's like even most extreme things in the universe can have a role to play in the grand scheme of things. It's amazing.
And as we learn more about black holes, we're sure to discover even more surprises about how they impact the universe we call home.
This whole deep dive has been incredible. It really makes you realize that black holes aren't just these far-off, abstract things. They're real, they're powerful, and they're shaping the universe around us in ways we're only beginning to understand.
And they're not just destructive forces, they're also incredible tools for scientific discovery. By studying them, we're pushing the boundaries of what we know about gravity, about space-time, about the very nature of reality itself.
And who knows what other secrets they hold, waiting for us to uncover them.
The future of black hole research is definitely bright, full of exciting possibilities. I can't wait to see what we discover next.
It's kind of crazy to think that something like a black hole, something that seems so destructive, could actually help us understand, like, the biggest mysteries of the universe. We've already talked about the information paradox and the singularity, but what other areas are scientists looking at when it comes to black holes?
Well, one area that's really, really exciting is gravitational waves. These ripples in space-time. Einstein predicted them over 100 years ago, and we finally detected them back in 2015.
Right, gravitational waves. I remember hearing about that. It was a big deal. But how do black holes fit into all of this?
A lot of those gravitational waves, they're actually coming from black hole mergers. When two black holes collide, it's such a powerful event. It sends these ripples, these waves, through the very fabric of space-time.
It's mind-blowing. We can actually detect those ripples from events happening billions of light years away.
It's pretty incredible, right? And by studying those waves, we can actually learn a lot about the black holes that created them, like their mass, how fast they were spinning, how they interacted. It's like we're listening to the universe, hearing these cosmic sounds that we never could before.
So it's like a whole new way of looking at the universe, listening to it, instead of just seeing it.
Exactly. And it's not just about confirming what Einstein said either. These gravitational waves, they're revealing new information about black holes. Like, we're finding black holes with masses we never thought possible. It's like a whole new era of black hole astronomy.
I remember all the excitement around that first image of a black hole, the event horizon. Can we expect more of those kinds of images in the future?
Oh, definitely. We've got new telescopes coming online, like the James Webb Space Telescope, and the Event Horizon Telescope is getting some serious upgrades too, so we're going to see even sharper images, way more detail.
So we'll be able to see these cosmic monsters even better. Maybe even see how the accretion disks and the jets are behaving in real time.
That's the idea. And it's not just about pretty pictures. These observations, they're going to help us answer some really fundamental questions about black holes. How they grow, how they affect their surroundings, how they influence the evolution of galaxies.
It's amazing to think about. We started off thinking of black holes as these destructive monsters, but now we're seeing them as these powerful tools to help us understand the universe. But, one thing I've been wondering about, what about dark matter? Does that have anything to do with black holes?
That's a great question, and it's something scientists are definitely looking into. Dark matter is still a huge mystery, but some researchers think that black holes might have played a role in how it's distributed throughout the universe.
So black holes could have helped shape the invisible scaffolding of the universe, the dark matter that we can't even see.
It's a possibility, yeah. And another idea is that dark matter particles themselves might be interacting with black holes in ways we don't understand yet, maybe leaving behind some kind of trace, some signature that we could detect.
So it's like using black holes to study dark matter, to try and understand something that's completely invisible to us.
Exactly. Black hole research often leads to these connections. It helps us explore other big questions in cosmology and physics. It makes us think about the universe in new ways.
Well, this whole conversation has been absolutely incredible. It feels like we've gone on a journey through the most extreme and mysterious parts of the universe.
It's been a real pleasure exploring this with you. Black holes, they're so awe-inspiring. They really challenge our understanding of the cosmos, and they keep raising more questions than they answer.
So what's the one thing you'd want our listeners to take away from this deep dive? What should they be thinking about when they look up at the night sky?
I think the biggest thing to remember is that black holes, yeah, they have this reputation as destructive forces, but they're also essential parts of the universe. They play a crucial role in how galaxies evolve. They push us to expand our knowledge, and they inspire us to ask the biggest questions we can possibly imagine about the nature of reality itself.
And even though they seem distant and mysterious, they're still impacting the universe around us, shaping the cosmos in ways we're just beginning to grasp.
That's a beautiful way to put it. Black holes remind us that the universe is full of wonder and mystery, and that there's always more to discover, always more to learn.
I couldn't agree more. Well, thanks for taking us on this incredible deep dive. It's been amazing.
The pleasure was all mine. Really enjoyed it.
And to all our listeners, keep looking up, keep asking questions, and until next time, this has been The Deep Dive.